So this video provides some additional insights into the definition of ergodicity as defined by Singleton. That is this slide in the script, where basically stated that, as mentioned in the lecture, stationarity would not be sufficient to have a law of a large number working for us. We need this notion of ergodicity that we need to invoke. The definition of singletons is different from what we see in Hamilton's or Hayashi's book, in that there is this reference of the random variables in the stochastic process to these omegas that we're going to see here in the notation. So the question is, what do these omegas mean? Where do they come from? Obviously, they are elements of the big omega thing that we have down there, and that's not easily understood. So in order to grasp the idea of Singleton's definition of ergodicity, we need to consider concept for measure theory, something that we've dealt with in the math prep class, but I'm aware of the fact that this is not something that is part of the standard curriculum in bachelor studies. So here's some additional information on that. So in order to understand this notion of ergodicity in singletons, we really have to go back to this notion of a probability space, a Kolmogorov probability space. This is a concept that was developed in the 1930s by the Russian statistician Kolmogorov, and his idea is to start the fundamentals of probability theory by defining a triple, and this triple consists of a set which is called omega, which we refer to as the sample space, and that sample space contains all possible outcomes, so-called elementary events, of a random experiment. The elements of these of this set or this space are typically denoted by omega, small omega, which is where the notion of singletons comes from. So it's best explained by a simple example that you already had in the prep course. So suppose you're considering the random experiment of tossing a coin twice, and this coin can show head or tail, right? H for head, T for tail. So the elementary events collected in the sample space would be 4, right? We would have the outcome that first comes head, then comes tail, or first comes tail, then comes head, or head comes and then it comes again, or tail comes and tail comes again. These are the 4 elementary events associated with that experiment. Now what we do then is, what Kolmogorov suggests then, is to construct from these elementary events events which are interesting to assign probabilities to. For instance, we could be interested in the event head comes at least once. Okay, and that would be transferred into a set, and that set would consist of elementary events. So we would define this event by collecting all elementary events which lead to this event coming true. So it would be, okay, head or tail. Head and tail, that would be meaning, okay, head comes once. Or first comes tail, then comes head, or head and head comes. Okay, so that would be an event over which we want to assign a probability to. Now what we're going to do is we can select all these events which we are interested in a set of events. This is denoted with a stylized F, and this object is referred to as a so-called sigma algebra. Okay, it's a set of events, and this set of events must have certain properties. So for instance, if you take unions and intersections of the events which are collected in this F set, you have to end up in the set again. So this set has to be closed under union and under intersection of events. That's a technical term. We're not going to be so much concerned about sigma algebras from now on, but we need to write it down in order to sort of complete the probability space a la Kolmogorov. And then what we have is a probability measure, P, that takes as an input one event out of F and assigns a probability to it. And this triple is associated with the notion of a probability, of a Kolmogorov probability space. So P would be a probability measure. Okay, and now random variables are defined on that probability space. So, for instance, we could be interested in a random variable which I would like to denote x1, and this x1 in words should give me the number of heads that show up in that experiment. So what I would do is I would take as an input argument an elementary event, and as a result I would get a real number, and that real number would be the number of heads that I get when I conduct the experiment. So example, x1 evaluated at the elementary event, first comes head, then comes tail, would return a 1. And x1 evaluated at the elementary event, head comes twice, would give me a 2. Okay. I could also consider another random variable. We call it x2, and the x2 random variable could be maybe the number of tails that show up. And analogically, we would have x2 evaluated at ht, which would give me a 1, and x2 evaluated at h comes twice would be 0. No tails show up. And this little example makes clear how random variables are conceived of. They are actually functions, right? Functions that map from one set, one space to the other, and the sets or spaces which are mapped into, which are brought together here, are the sample space omega and a set of real numbers. In the present case, we would have two random variables, so we would have a mapping from E omega into r to the square. So formally, I have a vector of random variables, x underscore, and this underscore indicates a vector here. And what I'm going to do here is I'm going to collect the two random variables in that vector. Okay, so that's basically a vector-valued function, and this function takes as an argument one element out of the sample space omega. So we have to do it with a function that maps from omega into r to the square, and it implies that I'm going to take one omega out, small omega out of the big omega, and what I get is I evaluate x1 at this omega and get an x1 out of it, and I evaluate x2 at this omega and I get an x2 out of it, a realization of the random variable. So I write this in a vector, okay, and this is what the function does formally. Okay, and that's it. These are fundamental concepts, fundamental notions of measure theory and basic probability theory. There's much to be said about the random variable being a proper random variable, that is, it has to have a proper cumulative distribution function, but we can omit that issue for the time being. And what I've done is I've collected some results, some ideas associated with the notion of probability spaces in a little PDF document, which I'm going to put on Elias. And in this document, you can read up some of the notions I just talked about. So here's the PDF. It's called Measure Theoretical Basis of Mathematical Statistics, a somewhat non-formal summary which expresses a bit the fundamental ideas behind those probability spaces. So check Elias out, read through it, and you get some explanations. Now, what's done in Singleton's quote is that he applies this notion of a probability space and the construction of random variables to a time series context. Now, as we remember, for us, time series are realizations of stochastic processes, and stochastic processes are vectors of random variables which are indexed by time, or sequences of random variables which are indexed by time. So in a time series context, we may ask the question, what actually is omega here? What is the sample space here? Right? What is the equivalent of this sample space that we have for this coin tossing example here? And what is the equivalent of this mapping from omega into the set of real numbers? Now, what I like you to think of is that we have still a vector of random variables to be considered, and as usual, talking about probability spaces, a random variable is a mapping from omega into the set of real numbers, and in the present context, it would be such that we have this vector of random variables, x1, x2, and here comes big T, which makes clear that these random variables are actually the random variables in a stochastic process. These guys are indexed by time, and I'm going to collect them in a vector. It's very similar to what I've done here, right, in the coin tossing example. We may also want to consider the situation that this vector has not just t elements, but in Hayashi's notion, there may be actually a vector that contains infinitely many elements. So something like that. Okay. So the random variables in my stochastic process. This process starts somewhere in the infinite past, goes on until infinity. That would be a collection of random variables that we considered. And so we have this mapping from omega into r to the t-dimensional set of real numbers, or maybe into r infinity when we deal with Hamilton's idea of a stochastic process, right? So that would be a definition of a random vector. So you would have this omega small omega out of the big omega. We take this thing, evaluate x1 at omega, evaluate xt at omega, and that returns x1, x2, xt, okay, and that would be basically the realizations, or one realization of the random variables in my stochastic process. Okay, and this is how we basically conceive of a sequence of random variables which are indexed by time. And what you should know and note here and really keep in mind is one draw of the sample space omega generates many realizations, or the realizations of many random variables. Or let's put it like that: generates a realization of the random variables in the stochastic process. Okay, that's something to grasp here. It's one draw from omega, big omega, that generates realizations of these big T random variables that we have here. Okay, and I'd like to illustrate that notion, this idea, in a little graph, and that is going to be that I'm going to show in the second part of that video. So we close it for the time being. You can watch this video, try to get the idea. Then comes the second part of this video that you can watch, and basically then we're trying to get closer to this idea of Singleton's where measured theoretical concepts are applied to time series analysis.